Okay, so we can see that this question is asking us to calculate the formal charge on each atom in each of the possible Lewis structures for the thiocyanate ion, SCN- as shown. And then it's asking us which of the three structures is best based on formal charges and why. So formal charge represents the distribution of charges due to bonding within a molecule. And in order to calculate this formal charge, you must account for all electrons contributed to the molecule both as bonds and as lone pairs. As we can see right here, formal charge is calculated using a given equation. In this case, formal charge is equal to the number of valence electrons of the atom minus the number of lone pair electrons plus 1/2 the number of bonding electrons. This 1/2 comes from the fact that in a bond, 2 electrons are being shared between 2 atoms. So I've gone ahead and shown that sulfur has 6 valence electrons, carbon has 4, and nitrogen has 5. This comes from the periodic table, as you can see. And then with this information, we can go ahead and calculate our formal charges. So starting with sulfur over here, we can see that we start with having 6 valence electrons, from which we are subtracting there are 1, 2, 3, 4 lone pair electrons plus 1/2 the number of bonding electrons. So since we have 2 bonds, that's going to be 4 bonding electrons, which will mean we are subtracting from the 6 initial valence electrons, 4 plus 2, which is 6, which gives us a formal charge of 0. For carbon, we can see that there are no lone pairs on the atom, but there are 4 bonds, which means we're going to have 1/2 of 8 bonding electrons, and 1/2 of 8 is 4, so 4 minus 4 is again 0. For nitrogen, we can see that starting with 5 valence electrons, we have 4 lone pair electrons plus 2 bonds, so 1/2 of 4 bonding electrons. And this gives us 4 plus 2. Subtracting 6 from 5 gives us a negative charge of 1. We can then go ahead and do this for each of the molecules. So over here for sulfur, we see that we start with 6 lone pair electrons with 1 bond. So we'll have 1/2 of 2, which is 1. And because we're subtracting 7 from 6, this atom will have a -1 formal charge. Carbon, again, has no lone pairs and 4 bonds, which means 1/2 of 8 bonding electrons is 4, so 4 minus 4 is 0. Nitrogen, in this case, starts with only 2 lone pair electrons, and we have 3 bonds, so 6 bonding electrons, and 1/2 of 6 is 3. So subtracting this, we end up with a formal charge of 0 on nitrogen for this representation. Finally, on this third structure, we can see that we start for sulfur with 2 lone pair electrons plus 1/2 of the 6 bonding electrons, so 3. And subtracting 5 from 6, we end up with a +1 charge. For carbon, we again have no lone pairs and 4 bonds, so 4 bonding electrons that we will have contributing, because 1/2 of 8 is 4. So again, there's going to be a 0 charge on that carbon. Nitrogen, in this case, starts with 6 lone pair electrons plus 1/2 of the bonding electrons, which in this case there's only 1 bond, so 2 bonding electrons, so 1 contribution. And subtracting 7 from 5, we end up with a -2 charge. Now, once we've calculated these charges, we need to know what to do with them. In order to determine the best structure, we're going to need to look at which atom in the molecule is the most electronegative, and that's what we're going to want our negative charge to be on. Now, another consideration is the fact that we want to have the most electronegative atom with the negative charge, and we want these charges to be as close to a net 0 as possible. So just on that alone, we can see that the third structure is probably pretty unlikely to be what we have. So moving over here, we have a table with the electronegativity values. So if we go and look at sulfur, it has a 2.58 value, carbon has 2.55, and nitrogen has 3.04. Nitrogen clearly has the highest electronegativity value, and because our first structure right here has the negative charge on nitrogen, we know that that is going to be the best choice for our structure. Structure 1 is the best because the charge, the charge is on the most electronegative atom, in this case, nitrogen.